streaming. Faut que ça marche pas pour le moment. Ah bah oui, c'est parce qu'il n'est pas encore 4 heures. C'est... Voilà, we are online. Sauf qu'on n'a pas la caméra encore. Hello everybody, sorry, we're trying to solve some minor, hopefully, technical issues. Why is the camera not working? Start recording, camera. Settings. Ça marchait tout à l'heure. Ah bah voilà. Ah oui, il y a un décalage. Tu veux que je fasse une petite annonce pendant que tu écris le tableau, Grégoire?
Alright, hello everybody. It's the first time we attempt to stream a seminar, so in Henri technique, so you can have good luck. I'm trying my best. It seems that it's working. It's kind of normal. I'm expecting that we're together, right? To think and work, and we're very lucky to have Henri with present to us that aspect. Electronic theory is a great information theory. So now I go back and let Grégoire take over.
Take care everybody being here, so speaking in here, so English, French, let's speak on English. So as normal, like trying to do a new form seminar, starting on I know around the mathematical models of consciousness, so I try to go into the details of the models, so it's a study group, like center study group. So they tend to intervene to ask you have more information on something, or you like to paper. Also, it would be good to have somebody that takes notes. So I read somebody that would like to take notes for like you kind of by this side, because I'd like to have some let's say PDF photos, so that you can share. So who would like to write the notes? Okay,
I'm gonna do everything. All right, you do. Excellent.
Thank you very much. So next time we're talking. So the definition of today is IIT and the formalism of IIT. So IIT papers by Kleiner and integrated information theory. I think this is a very clear paper, which is not obvious for let's say a college student that there's an IIT, so a lot of specifications which I'm not like an expert about, and some of them not very good at all. Necessarily the best person to talk about IIT, but the aim of the study group is try to learn more about IIT. And the second one, which is IIT 4.0, which is the most recent version of IIT. And for me, it gets unclear in terms of compatibility between like which paper and second one, especially bias. So let's start now. So the first part will be of definitions. Especially about kernels and then use variables. So probabilities. Part issue. Second part will be about how interactions and how to come to the solution of all this. So next thing is all. Can you guys write this? All this. Try to give a quantity of what something is if there's a wholeness of a system. And the third part will be to simplify,
which is a quantity that allows you to define the big file. So both are
heights.
Okay,
So let's start now. Part one. Okay, so we have a finite set x. We will know p of x, the set of coordinate integers. And x, in other words, that's a function of x. And that's some of x and x. Okay. Then trivial, probably trivial. T next to x is simply a function that for any x associates tx with tx. So in other words, what we are trying to do is just for any two. So for any x prime x in the x, we will denote the express as tx prime x. So it's a function over x and x over x squared. So x is a coordinate set such that Okay, so here we go for some particular spaces x, which are product of identity particles. So let's consider a set, finite set. S, and for each I in S, we will consider a space, finite space. And we will call x as the product of I inside S. Okay, so this is the notation. Now, for any inside S, so any collection of I and elementary particles inside S, we will denote XA as the tuple for all I in A. And similarly, the set of XA's denoted x again. Denoted x again. So here nothing. Nothing much. So here's just notation. So if you have questions about notations.
What is x?
So xi and then big xi.
Yeah, the big x side.
So for example, consider you let's say two variables. So we'll say weight and height. So that's x1, x2. And for each individual, you can have a value of weight and you can have a value of height. So now you have n variables. And they don't necessarily get in the same space.
So the space is just where the value is range.
Exactly.
And the probability kernel just looks like a Markov chain.
That's not, I mean, it's the, so it depends what you mean by it. You can build a Markov chain from a probability kernel. It's just a probability kernel, a Markov kernel, and has stochastic map. Other questions? So are you all familiar with this notation product? Product means all the couples. So basically you something like this. You take for any I and N, so I and N you take it. You can take A, take S and O2. So for example, weight and height, and you can take A1, for example, subset. Then you have X1, which corresponds to the weight. And then the couple is weight and height of two particles. And then you have N modalities and types of particles. Then you have the tuple, so big list. of possible values of your bar. Collection of values. Okay. So
So first proposition,
for any Q in this
side of S,
one can define probability distribution bar x times x. So what one can do? Can you find P of x S?
Okay,
notes, so space P is a multiplication of x times,
and we will note the first variable as x1, and then the second as x2. In other words, we have two projections, and the second, first and the second. And the first one is
the second is x.
So
why do we do this? We do this because we want to introduce the notion of conditional execution. So now we'll introduce what conditional execution is. Consider y
and then y. Then for any inside of prime, you can define any function. F from the right function. You can define conditional execution with respect to on Excel as a sum of the y bar in y bar. Just one second. Y bar x over sum y bar f. Let's see. The A bars is definition.
It's very pedestrian way to let's only 1 hour you get the idea. It's not obvious like it took me more than 10 or 20 hours to really get it. So I think it's a presentation like where about the minimum amount of patients. And then if you take the time, you can take 30 minutes to go into the phases. After all, the rest is very simple. Okay, so for any distribution, Q and TX, S, I took Y because I'm going to define conditional expectation over X times F. over the space x times x, so y equals x times x for a certain particle. So for a q inside of x a, which is s b s, I will define this kernel a b So I will get the proposition and then I will do example say what this is and why we use. Position T here I will get S now for n over the sum of x bar 1 2 Okay, so now and then the question of what we're doing. So basically, you have a kernel T that tells you to calculate x on the set to x on the set. So you have T now, what you consider is you only want to look at the effect of a certain subset of variables. So let's say up to x and a, and then another subset of variable, like b, x and b, and then define the t that only goes from x1 times x and a to x1 times So this you want to do it for any couple of a. So you want to look at the effect of this kernel on the collection of particles. So what is the effect of the collection of particles A on the collection of particles B? You have a way, so this is a way to evolve from one set S to another one. And you want to consider only a sub-collection of variables at the start. A sub-collection of variables at the end. And see the effect of the sub-collection of variables at the start. So for example, if you know that you calculate weight, height to degrees, and you only want to know what happens if you want to calculate weight in degrees, how do you do it? So you have a kernel that allows you to tell you weight and height, how it's related to degrees. And now you want to calculate height, how would you do it? So this you cannot do it if you don't have that priori on the space you started from. So if you don't have this distribution over x's. And this is TAB. Depends on the priori. It's exactly what is defined here. So the way of defining it is to look at the conditional expectation with respect to SA, and then you marginalize, you take away the effect of all the other particles. And this is what they do in IIT for particular distribution, particular fire, look at the uniform distribution in excess. It means it takes the same probability for any set in excess. Okay. So now I want to give you an example.
Is there a reason why?
Yeah.
When you calculate the conventional expectation function, why do you rule out that A can only go to values in A bar?
So is your question why doesn't depend on X? And only on XA bar?
When you do the sum, you rule out A, right? You only go in Y A bar, both above and below. I was just wondering if there's a reason here.
This is the definition of the conditional expectation. So the conditional expectation is you basically fix XA and look what happens probabilistically when you fix XA. So you look at all the events, but you always fix XA. What happens is that the probability distribution you have here, when you fix XA, is not a measure. It's not a probability measure. It doesn't sum to 1. So you need to divide it by the weight that there is in XA. And then you just do the expectation. So yeah. Okay, so maybe we can do an example. Okay, let's do an example. So that's the end of the first part. I'll try to end every part with an example. So we consider x equals 1, 2, and xa can be equal to 0, 1. It's the same for all I. So x0. Now you take a, so you have t, that basically goes from send value of xi, x2 onto distributions that depend on xi, x1, x2. But you're interested only on the effect of A equals 1 on B equals 2. So you add x1, x2, x1, x2, and you only want to look at the effect of this on this through T. T, you can see it as a causality link. It's basically telling you what is the effect of x1, x2 on the next occurrence of x1, x2. And then I want just to be able to say what is the consequence of x1 at time t to the consequence only on x2 time t plus 1. So if you take Q to be the uniform distribution, so Q of 0 is 1/2 and on 1 is 1/2, then T, so now I'll drop the Q when it's, because I will consider only the uniform distribution, over x2, x1, it's equal to simply, so you need to sum over T, so x1, x2, y1, x2, x1, y2. Okay. So the distribution is one. What is the uniform distribution here? So I said 1, 1. Sorry, it's start q0, 0 equals q0, 1 equals q1, 0 equals q1, 1 equals 1 4. So here we have 1 4. And under
Grégoire, we just have some folks that have a hard time to hear you. First, there was some issue with echo, sorry to interrupt, but apparently Leonor is saying that when you are turned toward the camera, she hears much better. So
Okay.
just raise your voice, speak loud.
Okay.
Thank you much, and we're going to see.
Okay. And then you just sum over x y2 1 over 4. So 1/2. And here you have y1 and y2. So this is the explicit definition of TAB. This is the explicit definition for this example. So that's the end of the first part. So do you have questions? Like, do you find the format of the presentation good or not good? Like, you can don't hesitate to interrupt, and it's open. No questions? Is it clear for everybody?
Well, there would be questions from the people online, but I haven't enabled the chat, so they're communicating with me, and I don't know how to do that. I promise it will be better next time. Leonor is asking, is there a way to comment online? E.g., should be T x toward P the x, not T x toward x. This one.
Where?
This. Look at the email.
No, because the notation T of x2x is a notation I give in the category of, so it's the Giry monad. So there's in the category of if you take measurable spaces and you allow to have morphisms which are probability kernels, basically the notation Tx towards x means a function that sends x to a probability distribution. That's why when I define Tx, when I define Tx, when I said this, I said this is a function that sends something like this. I mean, it's because I use this as a convention of a morphism from x to x, to see it as a kernel from x to x. I mean, I'm not saying that it's a function, but okay, it's an imprecision that I should have stated. But it's a stochastic map, so it sends to any x a distribution on an x. So for example, it can be for sensors, it can be, I think that I'm looking at this point, but in fact, my sensor is uncertain, so there's a little uncertainty around the point I'm looking at, so each point corresponds to a certain uncertainty around the point where I am. For example, a motion of a small variance around the point. Okay, so why do we do all this? So the second part. So because this will be useful to allow to define the notion of wholeness. So there are other questions or not?
Not so far. I'm fascinated with the chat.
So we want to define the notion of wholeness, and the notion of wholeness is how much is a bit of something intrinsically interacting with its sub-elements, and compared to if I dissociate sub-elements, how much do they interact between each other? So, like, I want to be able to say I have a big set of components that are interacting, and I want to say that the interaction is whole if I cannot cut it in sub-pieces that are interacting only between each other. So to do this, I need to be able to say from some notion of interaction to define the notion of cutting out something. And this is what I just did before. So this is what we'll use to define the notion of wholeness. Okay.
I have a question.
Yeah.
So this notion of wholeness, comes with the notion of parts in it?
Yeah. Yeah, exactly. It's how much you can separate the interaction between the sub-elements as interaction only between them into such certain parts. So I mean, like, if you can cut away, can you in the interaction of your elements, so xi, can you cut them away inside of blocks where they interact only inside of these blocks? And this is what, like, IIT is, like, the fundamental quantity is based on how much your interaction is not an interaction that is built from interaction of blocks. Okay, so this is exactly what we'll define now. So we'll just repeat it, but more formally. Great, so we said that we started with in space x up to x1, x1, and 1 plus 1. Makes sense, so we have a collection of variables, we have t. And we want to say that how do we differentiate this interaction with this one? The one that goes from here to here, and from here to here. So this is A, B, A bar, B bar. And here is the T that we defined before. So TSA, TSAB, TSA bar, B bar. So we want to compare this to the map that doesn't dissociate both. Okay, so first we need to be able to compare them, we need to build from this tuple a kernel so that we can, on the whole system, so that we can compare it to T. So the way we'll do it is that we'll do the product of the two kernels. So definition. So T, so for any A and B inside of S, TS A bar, I will take this notation B bar over XB prime, XB bar prime, XA prime, XA, sorry, XA bar. So for XB, XB bar inside of XS and XA, XA bar inside of XS. This we will define it as the product TS AB X times B XA times TS A bar B bar X B bar prime XA bar, and I will note it as TSAB TS A bar B bar. Okay. So this is simply what I'm doing is I'm cutting the variables. I'm looking at how one block interacts on the other one. So we said that was possible by looking at the conditional expectation for Q, a distribution that is uniform. We suppose that Q is uniform, is what internally they do. And then we can do the same for A bar and B bar. And we want to compare the evolution of this one to this one and this one to this one to the evolution of the whole. So to do this, we define this distribution which lives in the same space than TS. So now to compare them, we need to introduce a way of comparing them, and this we will simply call it a notion of a divergence, so just a way. So we'll introduce. So this I won't be formal about how we introduce it because there are several ways of doing it. And I will do something a bit sloppy about IIT that I will correct just after. So, to compare need to introduce a divergence D, so we denoted as, let's say, DTS, TSAB, TSA bar B, that is such that the smaller it is, the closer TS is to TSAB, TSA1. So that is informative here. Just this, so it's a function that you introduce inside of your way to compare kernels. And the only requirement that you have is that there's a notion of divergence, which is it computes how far I am from the distribution. So how far this is from this. And recall this is the consequence of the actions of T on its parts. And comparing this to this is comparing how far T is from only considering that the evolution comes from sub-blocks inside of the particles. So this quantity accounts for a notion of wholeness of T. If you allow it to vary on all the partitions that you consider. And this is exactly what they do. Okay. So do you have some questions here? Any questions?
So for the notion of wholeness, it's not just the parts, but their interactions is crucial.
It's the way your system, how far your system that is evolving, its evolution is not given by the way its subparts are evolving. Like you cannot see if you want to have something that is whole, you cannot cut it as the evolution of your system as there are subsystems that are evolving independently.
It's a bit of a synchronization thing. It reminds me of the global workspace. It's a bit the same kind of giving to consciousness a role of synchronizing all these different processes. Is it a little bit?
I don't know. Maybe you can say more about it.
Yeah, global workspace theory, from what I understood, is from Bars and Change and Stanislas Dehaene worked on it as well. The idea is consciousness has the roles of synchronizing all these processes that otherwise aren't synchronized. And this is where we're aware of stuff. That's like the basic thing, and then after there's so many developments, and it's a lot of theory of the brain and neurons and how, there's a lot to say about that. The basic is that, which reminds me of what you're saying. Like the divergence is how much it's not synchronized, right?
Yeah.
I mean, but here, let's say you had a situation with a covariance between your n variables that was such that basically they would be totally identical, they would be perfectly synchronized. How would behave your divergence? How would behave the quantity that you are introducing? If it was, fully correlated.
We need a fully correlated.
Well, if basically all the connections between the variable would be such that basically they would be behaving exactly the same. So they would be fully synchronized to the limit. Imagine that all the variable would be fully synchronized. They would show exactly the same pattern.
So if you this would be zero.
Yeah, so that's not just synchronization. There is a notion of combination of kind of differentiation and synchronization. There's a notion of
it's a good point.
complexity. So it's somewhat different. If you think about it, when somebody has a generalized seizure, their brain is totally synchronized, and usually they lose some form of consciousness. So that's one argument that they use sometimes. So it's in between. It's not exactly in between. So, but you cannot reduce the whole of interactions to independent parts. But it's not either that everything is basically so covariant. That's the same thing. There is no information. I mean, if you know one of your variables, you know everything about the other ones. If it's fully synchronized, and that is not what that's formalism captures. It's quite essential to be fair to what they do.
Yeah, it's a really good. I think comments to what you were saying, which I didn't think about. It's really because it's so. I think that the idea behind it is because you try to have your evolution of your system not to be independent collection of evolutions of subsystems. So it's closer to the notion of independency between variables.
Okay. Independency and not synchronization.
Yeah.
Not synchronization. Yes, I get it. Okay.
Cool. So you have other questions? Because it's open study.
So would it be like fair to say that this wholeness is something that is like in progress or something that is in movement or change?
So so you have something that is changing, but what you want to be sure is that if you fix like a starting point and you look at the consequences one step after, that the consequence cannot be described as independent sub-components. So you still, like the way you see it is you fix one point. This is what I'm cheating about when I'm saying this, and this is what I'm going to say just after. This depends on the point, in fact, that you choose, which is the point which will have that value in terms of phi. But so it's just a way to say the consequence of the dynamics of at step from step t to t plus 1 is not an independent. It's not given by independent components. Like the dynamic is something that is induced globally and they cannot be cut into small pieces. But you need to start from the same point. What I'm saying, yeah, it's exactly what you were saying. But I mean, like more precisely, you need to fix one at the beginning, which is something. This is a bit more general.
Okay, so this wholeness is something that's already there, but it's also information, like information, like in progress.
Yeah.
Okay.
Here, it's more general because, like, if I put only this, I need to find a way to take more points. And for example, I can take the maximum volume or the minimum volume of the points. But here, it really depends on the stage you're from. Okay. So now I will denote for convenience theta over S, theta S, the collection of partitions of S union, digital union S, so two copies of S that do not intersect, so 1 up to n, 1 up to n. And I want the collections to be of the form A bar, B bar, the partition. So it's just exactly what we've been doing from the beginning, but just to give a notation. So here I have A, here I have A bar, here I have B, here I have B bar. Just to give a notation, and I might denote one element as theta. So the set of all these is theta S, and one element is theta, for example. Okay, and then something that is nice is this: I did everything for S, but now I can do it for any subparts of S. All the presentation I did up to now holds if I replace S by a subpart of S. T is well defined, the product is well defined. So this is what I will say just now. So, in particular, I will consider subparts, so M and P, where this is inside of X and this is inside of X. S, so it's S corresponding to, remember, 1 up to N, 1 up to N. This will be P, this will be N, for example, this will be T. But there's the idea that there's a dynamic from this set to this set, or at least the states associated to these sets. And I want to define the dynamic only for subparts, so all what we've been doing from the beginning with A and B. Now I will call it M and P, because this is also the notation of the article, the first article at the beginning of the presentation. And I will say that T, I restrict myself to T and P. I want it to be, so T and P, that goes from Xn to Xp, or let's say Txp is what you see as a function, which is defined as T, S, N, P. So we had T, Q, A, B, S, which was the restricted kernel to, you start with only variables in A and then you go with variables in B. I do the same, I just define like this. And now once I define this, I can take this as the starting kernel and then define everything that they defined before. Just in this setting now, when I have M and P, so for example, N is 1 up to 3, P is 2 up to 5, I have x1 times x2 is 3 as state space, x2 times x3 times x4 times x5. And the partitions I will consider inside of M and P will be A like this, for example, A equal 1, 2, and B equal 2, 3, for example. So I'm replaying the same game with S, but now I start with M and go to P. And M and P don't need to be the same. But with what I defined before, I can do it. Okay, so that's officially end of part 2. Okay. Okay, part 3. So as I said in the previous board, I cheated because I don't want to compare TS AB, but I want to do it for one fixed state from which I started. And so it doesn't change much. It's just something, it's a divergence that is contour, which is that you look at this compared to this. And now I will define the function phi, which is the first function of the IIT. Phi Pm for two subsets of x is a function that sends any point x and s. It's defined, sorry, phi. Okay, so phi Pm of x is the infinity over all the a inside of n, all the b inside of p. So this defines the couples AA bar, BB bar inside of theta and P, where theta and P were the partitions, but this time not for S, but for A inside of M and B inside of P, of the distance, of T, the divergence between T and XM, so the quantity that's just above, and TSAB X, so here XM, XA tensor TSA bar E bar XA bar. So this is one of the fundamental definitions of IIT. The small phi, and there will be the big phi. So basically, this is telling you that I want to look inside of my system at all the distance that is from the whole system to its dynamics induced by the parts, and I want to look at the one, the divided one that is closer to my dynamics. As I want to be able to say my dynamics does not come from dynamics of subparts, I will compare it to any subpart and take the one that is the closest to the whole dynamic. Okay? So from there, we started with one dynamic, T, and we divided and said, can the dynamic be induced by the dynamic on subparts? But this, we chose one subpart, one way to divide. Now we look at all the ways to divide, and want to be, as we want to have a notion of wholeness, we want to say which subparts describe the better the whole dynamic. So it is the one that will minimize this quantity. This is how far the whole is from the parts. And I want you to look at the one that is the closest. Because or else I'm not doing my good job. I could put something that is purely independent here. I could put something that is uniform. Of course, my T is not something that is uniform. It's something that has some shape, that gives some dynamics. So I want to be able to look at from the one that are the independent parts, so from independent evolutions, I want to be able to say, this independent evolution is the closest to my whole evolution. And this quantity quantifies this for any collection N and P inside of S. So here, I am only talking in IIT terms about the effect phi, and not the cos phi. And the reason is because I think it's simpler for presentation. So I'm only talking about the effect of phi. That doesn't change that much. I mean, if you understand this, then you can. I mean, you can understand all the rest. I mean, it's just focusing on the effect part. So phi of E. So now, you want to see M as, so here we're basically trying to compute the wholeness of the effect of M on P. How whole is the effect of M on P? So how is it far from the effect of M to subparts of P, for example? Or let's say if you cut M, you cut P, how is the effect of M on P close to the effects of the subparts of the subparts? But now, we want to introduce a quantity that depends only on M. So what is the maximum effect of M? What is the maximum whole effect of M? Because M is where we start from, P is the consequence, and we want to know what is the maximum whole effect of M. So then we want to introduce another quantity, which is phi star, phi max, of M, X, which is simply the maximum over the P, or the sub, max, okay. Over the P inside of S, of phi n P X. Okay. So this is the end of the part 3. So maybe if you have questions, or I can give an example, or let's tell me if you have questions. So here is really now we're inside IIT. I mean, now we're reaching IIT, and there's a fourth part which is defining the big phi. And then I'll tell you, take some caution about what I say because I'm not completely certain. But up to now, this is a small phi. So you have questions. I think it's a good point to maybe discuss about the quantities a bit more, or because like I told you, I'm not an expert on it. So.
Well, are there examples?
It's example just of how to, if you choose. So it's not. I mean, it's more. So I'm going to give example on particular case, but it's not an example on the data or anything. It's just because most of the time all the papers are very they use a lot of notation. So I think it's good to keep, because as it applies to any set S and XS, to keep it on a small example and to see how this is computed. So this is what I wanted to do. So okay, let's take an example then. Suppose you have M. So S, you start again with S equals 1 to 3. And you consider N equals 1, 2, T equals 2, 3. Okay, and now you take one theta. You say it's 1, 2, 2, 3. So this is A, this is A bar, this is B, this is B bar. And now, so if you recall, so I will tell you what phi p n is. So let's compute d. So what is this expression in this case? So what we're interested in is in d 1, 2 for 1x 1, 2, and here you go in 2, 3. And then you want to compare it to T, S, X, A, T, sorry, so T, here it was T, M, P, and here, M, P. Okay, and so you want to, so T, 1, 2, 3, X, 1, 2, 4, 1, and 2 times. So we will just, I'll write everything in this example and let's try to make it like write out the expression. So that at least if there's a mistake and someone who knows more about IIT can tell me this is where you're wrong. Okay. So here it's 1, 2, still 2, 3, X 2. Okay, let's do something like this. 1, 2. And here A bar 2 and B bar 3. And now X T. So T 1, 2, X 1, 2, 2, 3. So so I want to evaluate it on something. So what will I evaluate it on here? What will I put inside? Y, X. Here what do I put? So it depends only on 2, 3. So on the variables inside of 2, 3. So here is 2, 3. And here it's from the beginning 1, 2. Because remember that 1, 2, 3 goes to 1, 2, 3. And now I have M that is this, and D that is this. P that is this. Okay, so this, by definition, it was the sum of T, S, so we said S 1, 2, 3. So T, Y, T, Y bar 1, let's say, Y prime 1, let's say, Y 2, 3, X 1, 2, X prime 3. And then we said X 1 equals X2, so X3 equals 0, 1. So 1 over 8. The sum of the 1 I prime X3 prime over the sum of 1 over 8 for X I1 X3 prime in X3. So this is 1/4, so 1/4. And so if I'm not mistaken, I didn't prepare the example, but I'm a bit stressed, but if I'm not mistaken, you get that is this expression. Okay. So this is the first part here. So I tend to make a lot of mistakes when I write things like this, but so if you retake the expression that you have at the beginning, normally it gives you this. Okay, and so the other one. The other one is so T. So T. Let's do it for the first one. 1, 2, X 1, 2, 2, 3. 1, 2. So what does it depend on? Here, if I put Y and X. Yeah.
Sorry, yeah. All right.
No, maybe I'm not here, so.
No, that's not human.
And the thing is really technical. I mean, it's not really technical, but there's a lot of there's a lot of computation because it's more an algorithm. And I mean, I see it more as an algorithm. So you have a lot of you see in an algorithm you can call boxes or functions, and here if you like to write everything, it can be very, very long.
No, but that's why we are here. We want that type of level of analysis, even if, I mean, except a couple of people here, maybe we understand only a little bit of it. It's okay. That's because that's what we want. We want to learn, and we want people of your caliber to, help us understand theories.
So now the thing is, so I don't want to be mistaken. Okay, so let's do it like this. So this is, you take this one, and now you sum with respect to what you took away, and then you divide to with respect to what you took away here. So you sum over y1 prime. So here this one should depend on 1, 2, and this one should depend on 2, 3. So you took away 3, so you do x1 prime. 1 t 1 2 x 1 2 2 3. And then here you put y3 prime, y2 x 2 x1 prime. So here let's say y2 y3 prime, x1 prime, x1 x2 prime. Sorry. Then you put 1 over the set that you started from. So it's 1 over 4 because you have 2 configuration, and then you divide by 1 over 2. And you can do the same for the other one. And then you just do the product of this with the product of the other one. And the distance, I didn't tell you how you do it. So there are several ways. So some talk about Wasserstein. So in the first article, they talk about L1 Wasserstein distance that you can take. And in the article of Tononi, they use a very specific expression, which for me, I don't know if it's related to the one with Wasser, like the one referred to with the article of first article that I was mentioning with the Wasserstein distance, but I'm not very, I mean, I have difficulties understanding why it's a good quantity, but okay. But at least take it, take any d you want, anything. Like you can take, for example, L2 distance. Anything you think is right to say how far this measure is from this one. Okay, and so the last part for big phi is really, it's using all what we did here, putting it back inside a more complex system, and then getting the value back. So maybe okay, if you don't have any questions, I'm going to try to do the last part, and then we'll stop.
So you're not going to talk about IIT 4, version 4 today?
I mean, I don't understand it well enough to say the difference between this one and the one of the first article I was discussing. Yeah. Because the thing is that there are very specific Ds that are chosen.
I know.
And then the thing is so I'm not even sure, this is the last part of the big phi. I'm going to explain what I understood from the first article, from what I read also from other places, but I'm not even sure, I don't know if there's a consensus on how the big phi is defined, which read through all the articles. Maybe there is, and I don't understand, so I'm sorry about this, but maybe it can be a good thing to discuss it next time.
Yeah, I think it might be a good idea to have a session 2 that continues on IIT, because at the end, this is one of the prominent models that has some degrees of formality, I mean, not degrees, a lot of, let's say, formula and algorithmic expressions. There are questions about what theory is that about, but that's a different question. And so it's important to dig into that well enough, and to try to figure out a bit of what's going on with the different versions. One of the big questions that a lot of the community is wondering is that, does that make really a difference? And what new? So I think it's worth using the time we need. So today you close where you want after a big phi if you want. And then maybe next time we'll schedule another one. And hopefully this time chat will be enabled and we'll have better audio quality. Now it's resolved. Thank you for everybody to help us with that. and we'll have more perhaps people from outside this room wanting to discuss and maybe contribute to, because they know better. If anybody knows better beyond the small core team of people around Tull. Okay, so go ahead.
So the last part might take like 10 to 20 minutes. So I don't know if we like.
Go ahead.
What do you want to do? You want to stop here and we go next time on Big Five, or you want to, how long do you have? Question.
I vote for continuing.
Now it's
Big
1
Five,
hour already.
because it will complete. You know, without Big Five here, there will be something missing.
Yeah, but okay. But
But
if it's
maybe if you have questions, we don't care. I mean, we can go on. You know, there is no schedule for the duration of the talk. Maybe we'll formalize that a bit more. But if you have any question here that is so pressing that you don't want to go on to Big Five. Big Five.
so you want to, as you wish, you want to stay?
Go ahead.
Okay.
Do it.
So we'll part 4, Big 5. So this is my understanding from what I read. So up to now, I think I better, it's okay, maybe I made a mistake, that can happen. Here is still, like, I'm going to present what I understood from the first paper, which I think is what is in the first paper, so that's okay. But now, with respect to other papers of autonomy, I'm not, for me it's difficult to make the link.
Maybe you want to say a couple of words about the first paper. It's
And that's a very good paper.
it's Johannes Kleiner, right?
Yes,
So it's yeah, I know. So it's one of the good formalization and summary of, you know, that is well written of IIT. So, but that he is not from the group of autonomy. He's from the Oxford.
There's also Tull.
Yeah, in it. So those are not people that work directly with the group of autonomy, and they try to take whatever they could get from it and give it, you know, in good form. Correct? Right.
Okay, so now any n that is inside of S, we will not see it as a set, but as a collection of subsets of n. So we will associate to any n the collection of subsets of n. So this is all the sets A that are inside. Okay, so this is based. So you recall what I said at the previous time? So just before, I said I had TPN, TNP, X that depends on N, Xn, and I compare it to TNP. So I did the min, inf, over the partitions, AE, inside of T, TP, A, B, T, N, X, N, X, A, X, A bar, P, A bar. I did the inf, and then I did the sub over P. So I will denote psi M X, the function that associates the P that is the argmax, so the sum arg sub, the argmax, because it doesn't exist on sub. The argmax of this quantity. So this is so this is a certain P star. Okay. Now what I want to do is to know how much. So we were discussing the wholeness of n, the dynamic between n and b, n and p. the maximum wholeness, so the maximum effect that n can have. So P is the one that is the maximum effect that n can have. Now we'll discuss how the wholeness holds when we look at subsets of n. So, now what we want to look at, so we want to compare for any b inside of psi mx, T A and A inside of n, T A X A psi and x with T A X A B times T A bar X A. Answer. It's like this, okay? And here B bar and so when you call notations. So before we had this, here an A and B, I will tell you, so this normally you can guess from what we did before, but I will tell you what it explicitly is. So TAXA psi mx, B is simply psi nx nt b a x a. So where you considered the partition on A and C mx, so this is your new n prime, and this is your new t prime. You consider the partition which is A and t, and the partition on P prime, which is B bar. So you have the evolution from A to psi mx that we defined. So the consequence of A on psi mx being the one of maximal consequence for n, and we want to cut only what happens at the end and compare. So at the beginning, we just choose as a partition to take everybody. Okay. So this is this one, and then I tensor it with the other one where I do it for B bar. So this expression here is a bit different from the one we saw before, because before we would have considered an A1. We would have considered A here, A1 here, and now I'm going to sort of choose notations. A1 here and A bar 1 here. This is what we had before. Now, from what I understand from the paper, you take this away, and so this one is defined by this, and the other one is defined by the same expression, but you replace B by B bar.
You replace what?
B by B bar.
Yeah.
Okay, and so now, this is the way that you compare the subparts to know how the subparts of N are maximally, let's say, whole. And say you want to know how whole the subparts of N are. Okay. And so you can define a quantity phi that depends on n, let's say on A, X, A, B, to be equal to, so phi star n, and we'll check after that, the sum over the, sorry, so that was a mistake. Of this quantity here. A star n x I'm getting confused. Oh, that's good. And, okay, b bar and here x. T xm b, and this depends on b side. Okay. So it's just a way to compute the wholeness of the sub. So now you want to redefine the notion of the wholeness of n that takes into account the wholeness of its subparts. And you're only allowed to look at the maximum interactions of the subpart on P. So you want to look at the maximum interaction you can have from n to subsets of x, and then you look at the consequence of the subparts of m on keeping the wholeness of consequences on P. So just 1 second. That's it. Okay. And then the last part is you want to look at the minimum of this. So the big phi is basically over nx, the minimum of phi of nxb, or b inside of phi nx, and if I understand well, psi of x is the sub over n of phi of x. So this is what I understand. So then you got it all. So there might be mistakes once again on the last part. I'm less confident, but I think it's a good thing to discuss about it maybe next time. So
may I ask a question?
Yeah.
You know, it's somewhat a complex. I don't want to say theory. I don't see any theorems, but it's a complex formulation, and it has to be because it's complex. Okay, but can you let's by analogy, you know, with all, you know, whatever is the distance you want to use as a measure, etc. What would you say for something that most of people, you know, in this community would easily understand? How does that relate to simple mutual information, for instance? Is there any relationship, or are we?
I mean, the way that
in other words, is there a way without betraying the theory to say, well, at the end, all of that is kind of just that, or not?
I think so. I will answer in a very political way. No, I mean, to be honest, I don't know. I think that there's what is very interesting is the fact of this notion of wholeness. So how far knowing how far a distribution is from independency is something that's well known. But the thing is, the way that they do it is there's a dynamic, and then you try to. This dynamic has more properties, which is that it has to be respect a certain form of wholeness. And then the way that they do it is very natural, because they say, okay, so the dynamic induced by its part is far away from the dynamic of the whole. So let's define the small phi. Looking maximally, like you look at the maximum causes that you can have from one maximum effect from one m. And then you try to say, is M also a good candidate? Because you want to cut it into parts, basically, and be sure that the parts, they keep the same property than M. So M that induces the best whole consequence at next step has to keep the same thing for its subsets, because basically, if you don't want to say I took an M that is too big, because you don't want to say that I added some variables to it, you want to add to be minimal in some way.
Like versus
the way I
entire,
understand it, maybe I'm mistaken.
versus to avoid like it grows to the entire universe. You
No,
mean?
because everything you can. So the thing is, knowing how far you are from the independent dynamics is something that depends on the space you start from. So what induces effect. And the thing is that you can be mistaken by taking too many variables as being effective.
Yeah.
And the thing is, then the second part is about how not to have this. The way I understand it is how not to have this. And this then defines a phi.
Yeah.
And this phi is with respect to the state S that you are experiencing. So it makes sense. Everything, all this, why they do it, and everything. I think it's, for me, it's something new. Yeah, of course. I mean, of course, it's something new about this. Yes, it's a way of. It's a way of putting things that, I mean, it's a model, it's an algorithm, so you need to put things that already exist, put them together, and then you get something, you want to describe something, and describe something that is something new, I think.
You don't think that a similar concepts were at play in other more classical quantities that were used in different fields, for instance, in different domain of application? It's new as a method of extracting some properties.
This way of doing this stuff is looking at one particular thing, which is you don't, and the first argument is you want a wholeness of the consequence of M on something. There's consequence and effect, but here we're considering a consequence and cause, but here we're considering only consequence. And so this you want to compute it, you can compute it, and then you want it to be a minimal, whereas here M has to be minimal in some sense, and you don't want to have taken too many N's. And so then this induces the second phi. And the only thing I say that I don't understand well, that I find I'm not very convinced about, is the shape, especially shape of D. So in the article, the first article, the shape of D is Wasserstein distance, which makes sense. I mean, like it's a way to compare. And the other one.
Can you repeat so that people can hear the
Wasserstein distance. Yeah. So in the second one, it's in the one of IIT 4. They do a trick to be able to select, the way I see it, a state inside of P so that they can look at the likelihood ratio with respect to the state, and then it becomes very messy, and it's difficult, for me it's difficult to interpret why they do this, because probably I don't have enough knowledge. Okay, so if you guys want to discuss...
So any question around? I mean, it's... It's okay. This is a lot to take on, and it's quite sophisticated. And thank you, Grégoire, because around myself, at least except perhaps Daniel Benkamp, I don't know anybody who could do that job that you did. And we're glad that we have you to run this seminar, and hopefully we'll learn a lot and make progress in our understanding of people's theory, of how they relate to each other formally or not. At the end of this series, we're going to try to put together a program and everything. We just started and it's a bit improvised. So for the people in the audience online, sorry for the sound at the beginning. Thank you for, with your help, I could resolve it. I couldn't even figure out how to enable the chat. So next time, hopefully it will be better. I'll get a mic that I can put on Grégoire. So we're going to make progress also on the technical side. Discussion.
No, I don't agree.
Not on you, whatever.
No, I don't agree. It's an open study group, and I think we should keep it open. Not like, I think should people read, for example, some papers, and we could discuss it. And
no, I totally agree. I'm just talking about technical issues that made you, some people sometimes have a hard time to hear you. But that's okay. Everything is just fine. So it's all my fault, my bad. Anyway, so next time perhaps, I mean, we'll keep posted people, of course, about what's going to happen. Next time we're probably going to continue on IIT or something like that.
And then if there's like anything you want to look at, so what's good is to have notes, because I think that there's no notes on the model of consciousness, mathematical models. So it would be nice to get some common notes so that you can share and send. Like this would be a reference, like for people to go if they want to learn about it.
Yeah.
So I think it's good to go into the details of the models and try to keep at least one version of IIT that is full and say we stop there. For example, IIT 3 or IIT 4. We don't cover next IITs. Or maybe this kind of notes exist, but I didn't see them. So I think this would be one of the goals, and then it would be also good so that we can interact. I know that some people know more maths than others, so I think 3 people know maths, maybe 4 or 5, I don't know. Maybe 6, maybe.
No, come on. No.
But I mean, like, it would be nice to have other people present also and discuss.
Yeah, and of course, what I meant is that I'm hoping that, you know, the courageous people that are attending online, like Leonard Bloom, Carl Friston was with us, will be able also to contribute to questions interactively, because you know, I'll make the chat working. So anyway, are we going to close for today?
Any
question, any comment, any suggestion, any recommendation?
The presentation. So maybe if you want to talk about it, discuss, we can discuss now.
Go ahead. I mean, I'll keep the thing streaming, it doesn't matter.
So I know a bit of math, but I understood everything. I didn't understand the interpretation of Big Five, and also Sir?
Are you okay to be on the camera? Or you don't want to?
Yeah, sure.
Yeah, okay, sorry.
Yeah, I didn't fully understand the interpretation of Big Five, and also if we could just say a few words on how that relates to psychology and consciousness. Yeah, that would be awesome.
Yeah, that's a good point. I think it's something maybe David, you know more about. For me,
yeah, but I don't.
I wouldn't be able to give a global response to this. Answer to this. I think for me, okay, I'll answer. One thing, I think it's about qualyas, maybe I'm mistaken, and about the way to describe them. So the quantity, the quantitativity of phenomenal experience, how to quantify qualia. So I think this is the way I see it.
Yeah, I mean, you can read the paper that we committed, and which is highly critical of it. So I'm a bit biased. So of course, I'm happy that we are trying to set up this seminar so that we want to just understand the theories. But if you hear me, I will just read a paper that we published recently with Björn Merker and Kenneth Williford and myself in behavioral and brain science about IIT, a case of mistaken identity. And it's, there are a lot of things that can be discussed about this paper, but that's not really the room here to discuss that. I'm not convinced at all by there are great intuitions in it. There are things that are important that capture aspects of the whole integration of, the phenomenal experience in some sense, in the sense that there is a wholeness, there is a complexity to it, etc. It starts from some, what they call phenomenological axioms, and then they translate that into some sort of postulates that can basically somewhat information theoretics, like inspired process. And they make this mapping between a few set of phenomenological, let's say, axiom, if we want to use their vocabulary, and this postulate that then translate into this sophisticated and sometimes difficult to grasp algorithm. But I would say, my only point really of criticism that I would maintain is that the axioms, so to speak, some of them are actually highly problematic and seems ad hoc to me, but that's something else. They are not specific enough. So they describe things in nature that you could apply that, of course, may be true to consciousness, but to me they are true to begin with, about many things. So no wonder that then, you can find using this type of approaches, very, very simple systems like, 2 photodiodes that have some interactions, or even now some folks talk about, protons in and of themselves having a phi that is not 0, so basically that supposedly, would match this notion or this basic notion of consciousness. So to me, it's like, okay, this is my impression, and I wish I would be convinced from the contrary, because I think that the team of Tononi and Giulio Tononi started something important back in the day when I was young, and I said that's what we need to do. But I think at this point, to me, it's a theory that lacks specificity.
But
it's not about consciousness.
What do they try to do? I mean, I think what is the aim? Because I think really the way I see it is to quantify qualia.
No, qualia, well, that's... it's
like
not just about qualia, because qualia, they don't really have they have hypotheses about how the specific detail of the causal structure that underline this kind of quantity or this kind of information integration might relate to, you know, sensory spectra, etc., etc.
I mean, what they want to do, the thing
Yeah.
aim.
Yeah. It's also constitutive. It's more general about, you know, the kind of a consciousness as something that constitutes an experience. They talk about a subjective point of view. I mean, I refer you to our article, but to me, it's really by analogy. It has a lot of issues.
Yeah, no, sure.
It doesn't capture to me enough of the phenomenology. Yeah. No, there will be issues in all of them, of course. But you ask me, I'm telling you for now. I think that my point with that, beyond the fact that it's a bit perhaps too sophisticated for what it should be, is that it's not specific enough. So therefore, it predicts too much. It says that everything but a few things is conscious, and to me, it reached something that, to some extent, is absurd. But that's to be discussed. That's my opinion. I'm an old guy now. I have a lot of biases, and so you guys, prove me wrong.
So you would agree with the fact that, because I think your question was, what is the aim? No, what they're trying to do. And I agree that there's the psychological.
Mine was bigger. Like, we have all these math, and it's wonderful. Like, how do they relate to, the more understandable features of consciousness, that aren't formal, like whether it's attention or phenomenal experience or whatever it is, right? Like, what's the link?
Well, here is what we can do. Next session, you're going to read some literature, and you're going to tell us what you think about it on this aspect. That would be very useful. And you are doing your PhD on mathematical model of consciousness, so certainly something you need to understand. So I can send you references, both from the people, and some criticism, and you can read and perhaps do a bit of an introduction on that. And then maybe Grégoire can continue on more mathematics. I think we can do that. Let's all contribute.
On the connection between their mathematical models and the actual psychological.
Yeah. No. Really what they say they want to achieve, and what we think now that we have a better understanding, thanks to Grégoire, of some aspect of the theory, what we think they do. But there is a very broad literature, and it's, we're going to see. Okay, anything else?
I mean, I don't know, I think it's not to be, we can stop, if you want to say something. But so this is more the kind of a bit formal presentation, but I think it's good to discuss. So the experiments also, how IIT has been experimented, what it can predict, what it can't, how. So there's something very difficult to relate for me, is the axioms of IIT and the model. So they have axioms, and they say from these axioms we can derive the model, their algorithm, which for me is not clear, because I find that it's very difficult the axioms are very and for me not difficult. So in terms of how they specify the system, so I had to underline something. So I think wholeness is something that is important. Qualia is something that is important. There was some sentences. There are some parts which I think that they can allow to predict some parts of the model, but I'm not convinced that all the axioms allow to do it. So that's also, I think, an interesting direction, because they always start with the axioms. Okay, great.
Yeah, and one of them is named the axiom of exclusion. I invite you, since you are both a mathematician and a philosopher, to deeply think about its ramification.
So do you have comments or?
Yeah. Are there any practical use of this kind of theory? Like IIT, is it used for specifying a system, a biological system, a society? What is the uses of this theory?
For me, I don't know enough. So I would say the thing is that there's. So I'm not an expert on IIT, but I would say that there's that they try to set up experiments, right?
Yeah, but the problem is that it's very hard to operationalize experiments.
But in practice, like, what do they have in practice in terms of, like, can they put it in the, like, how do they use it for functioning, for example, to predict some function? I think this is not the
well, and it's not necessarily the aim. The aim is deep. The aim is very deep. Is there something that is fundamental about consciousness that we can quantify, and that maybe we would need to add to a common understanding of physics, for instance? What? Without, necessarily leaving the realm of something we thought about within physics, is there a way of thinking about consciousness as something related to a fundamental quantity, if we can call that fundamental, like big phi, etc., of integrated information at the end, so to meet the theory about integrated information and not consciousness, but that's the aim. And of course, there is a history of the development of this theory that starts from reasoning about brain networks, interactions in the brain, and then it becomes more and more independent from that, and realize it could be more general and applied to other things. But then, in terms of the practicability to make predictions that would be specifically derived from the formalism, and then that you could operationalize experimentally, that's one of the issues. It's a bit about like string theory, if we want to take an analogy. It's not clear what specific prediction you could make, that you could build an experiment that would be really like, in physics, like in optics, you do an experiment, it's very well calibrated and it's kind of discriminant, and then you can really do model selection and exclude the model versus the other one. Here, at the end, often, number one, you cannot compute directly phi with empirical methods, so you need to use proxy measure. Why not? We'll do that. So it's often confirmatory in the experiment. Oh, this brain activity is compatible with that. And two, and second, they are sometimes obliged, and that's what they have done recently in a very big adversarial contest between the global workspace theory and IIT, to go towards very, 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 very indirect predictions, like that actually are not consequent from the theory itself, like, global workspace theory, Aladoan, involves, for long at least, I don't know if that's still the case, but the idea that you need in the brain, so we go back to the neural correlative consciousness, frontoparietal interaction. Whereas in the Todoni's version or view, so to speak, no, you don't need the frontal part. So then it becomes, okay, now whether or not for access consciousness or different type of experiment that you can, do as well as you can. These folks, they are good, no doubt about that, they do their best. Whether or not you can, test whether conscious experience or access or some aspect of consciousness, they will correlate with interaction between frontal and parietal region or not. And that's the way they, to the extent that I understand at this point, they only have been able to say, well, maybe actually integrated information theory is more right than global workspace theory, the neural global workspace theory, Aladean, which is a specification of global workspace theory. So, to me, there is no way at this point to, in principle and rigorously, to derive experimental design, except some things that are really proxies and very far away and so totally non-specific, that would allow us to say, oh yeah, that's right, that's really, really likely that this theory is true versus other theory ain't.
So it's more neurosciences. In fact, the experiments are more neuroscience.
Yeah, or in psychophysics, or you can do simulation, you can do various things, but then you
But there's some, like there's a list of them.
Oh, there are tons. They have a lot of grants, they publish a lot, they do, it's a lot of people working on that. But this is not like you could derive from the formalism you just expressed on the board a brain model or whatever that would give you a quantity you could actually measure with a specific physical unit. As you would do in physics. So it's whole by analogies, and as when you have a chain of analogies that is too long, and you lose completely, so you cannot conclude anything,
There's something that's very important in this model. You need a T to start with, the T kernel that goes from excess to excess. And the thing is, what I was thinking when I was reading these papers is, where do they get the T from? Most of the time, T could be a generated model or something like this, and so you need to learn it. And maybe, I don't know how they do it for the like you were saying, neurosciences experiments. Like in neurosciences, to be able to compute the phi, I don't want to say it, they need to have the T, the kernel to start with. So maybe this is like something they infer from data.
No, but it's impossible.
Or they
you can try to do some proxy.
Like how do they do? This would be nice to know how.
Well, but we can talk about that next time. But there are multiple ways. There have been, or other people have been doing it, and sometimes they use methods that involve computation of, interactions between brain parts, or like functional connectivity, more different measures of functional connectivity. And so you have a hypothesis. If IIT is true, therefore in this condition, I would expect more functional. I'm simplifying to make it. It's actually more sophisticated what they've done. I don't want to reduce the quality of their work, but basically it's a bit like that in terms of the logic of the epistemology of it. It's like, right, if that is true, even though I cannot measure it directly, then I would expect in such and such conditions to have that and that. But it's not. You totally lose specificity, and then it could be interpreted in a million ways. And also, I'm not sure what information we gain. And what we are trying to do here, modestly, because I'm sure we will fail, for sure I will fail, I cannot do it, I'm not good enough, I'm not advanced enough, is to start from theories, from formalism, and try to see what the theory actually tells us, and what it predicts, what can be derived from it, and whether the theory would entail experiments that would not be trivial or too indirect to be able to conclude. And of course, that's the hard work that we need to do and people need to do. If we really want to do mathematical model of consciousness, that has to become real theories. And that from within the theories, we can predict exactly what we should measure or how we should do it to test the theory. And that's not yet there, of course, because it's complex. So we do things that are very indirect, and therefore we publish a lot of papers and nobody agrees because there is no conclusion that is possible. That's my opinion. Again, I'm the old guy here, and I may be wrong. So do you mind if you're on the camera? I can move it away if you want.
Oh, that's okay.
Okay.
I just wanted to mention that personally, I got this feeling, I know too little about this whole thing, but I got this feeling that it could be very useful for us to understand what this wholeness means better, because I think this could give us the key to understand better how this can be applied or useful for understanding consciousness. And as I was listening to your explanation, it reminded me of this person, Henri Bortoft. Do you know?
I'm not sure, and I have a terrible memory.
I don't know so much either about this person, but because I wrote this paper about the whole. So maybe we can look into this a little bit more and.
Okay, can you maybe forward it to the
Your
group?
wholeness of nature?
Yeah, the whole.
No, it's like Bortoft, Henri Bortoft.
Yeah, Bortoft.
Yeah, it should have. I mean, one of the premises of this workbook, even though I'm really not competent for it, but is that it has to be mathematics already, or there is at least something that is formal we can work on. That's one of the constraints we want to impose upon ourselves. So we are open to all sorts of references, but we want to make sure that and I'm not sure if the case, that we don't drift away from actual mathematical work to be able to think rigorously about the problem towards things that are very interesting but are more fuzzy. The question here is, can we do a science on all these questions around consciousness? Some people try, and at least, with all the critical view I have of IIT, I have to acknowledge that the effort, the endeavor, is really commendable.
Well, anyways, the paper is this specific paper that I was thinking of was the whole counterfeit and authentic. And this could be interesting for us to understand more.
Okay.
Like what background they might have to come up with this model of that comes with this whole notion of wholeness. And Like, why do they talk about
Oh,
this at all?
But you can read that there is tons of reviews, excellent review paper about that, about the foundation, the let's say the conceptual, the phenomenological, and the rational foundation of IIT, written by, of course, the group Autonomy and people around it. You can also read the paper in BDS that we committed. Of course, it's a highly critical paper with Björn Merker. But some of it maybe we didn't do fully justice to some aspect or some detail, but I think we summarize a lot of things in it too. So there are papers definitely that are directly related to IIT that explain those premises and claims. Here, maybe it's wrong, but we did not want to start from that. We assume that people would know, or if they want to know about where the IIT comes from, or it has been grounded, or it was derived. We wanted to dig directly.
I think maybe we can do some kind of thing where we can share some references and check and definitely look into this. It's true that the seminar is more about the maths, but I think the math will go away very fast because. No, I mean, I don't know. I think there's a lot of work that's been done on neurogeometry. This is very nice. I think it would be nice to dig into it too. There's a global workspace. So I think this thing we need to also go into details on this.
Yeah, and of course, Leonard Bloom will have a lot to say about that. There is a lot of people that are trying to use quantum mechanical principle.
And that's what you to understand also. I think there's some work that is very formal on the quantum side, which is very. So I think it's nice to. I don't know how we can share. I would be very happy to read the paper. So if you could share all together references and.
I got this paper also from the mathematician who's working on that.
Yeah.
So that would be nice to read it and to check.
Yeah, for sure. But if we want to do justice to the premises and motivation of IIT, of course, you can find where they come from with the notion of wholeness. It's written a lot in their own paper. But that doesn't mean this is not interesting.
If we focus on IIT for the next sessions, maybe we should have one part which is exactly on the motivations of IIT, because we might have how we validated the experimentally. So it means that it shapes the thing around IIT. We dig everything around IIT, and then we stop and we do.
Okay. So, but if you're okay to help with that for next time, you don't have to, again, it's informal, it's okay. I mean, it must be terrible for people on the other side of the internet to listen to us, but hey, we do what we can. So you come and you go on the board, and we discuss, and that'll be interesting. But let's make sure, let's a guideline here, let's not move away too far from the math. Okay? All right, great. Thank you so much, everybody, and sorry for the, nothing is perfect.
Bye-bye.
All right.